Suppose we have a convergence series with terms a sub k for which we can apply the integral test. We've seen earlier that this means that if we define the function f of x so that at positive whole numbers, k, f of k is equal to the terms of our series a sub k, then that function f of x has to be positive, continuous, and decreasing. We also saw that with the integral test, when I can show that my series converges, I can't find the sum of the series through that test. So the next best thing is to try and approximate the sum of the series. So if we approximate the sum, let's call it S again, so that's the sum of the whole series. And if we approximate it by the sum of the first n terms, which we call S sub n, the error is, as we've denoted before, E sub n equals S minus S sub n equals the sum from n plus 1 to infinity of a sub k. And if I were to write out the terms, we see that that first term is a sub n plus 1, then a sub n plus 2, and then a sub n plus 3, and so on. What we'd like to look at here is how could I bound the resulting error? So I want to know, is my approximation a good one? And my hope is then that I have a good idea on how to bound that error. So in order to do that, let's try to illustrate this error in a picture. And it's going to be very similar to the pictures we saw with the integral test before. So how can we bound E sub n? And what I want to do here is draw rectangles with area equal to the terms of my series. That's exactly what we did with the integral test before. In order to do that, I'm going to start by drawing a general sketch of my f of x. So I just draw my axes here. This is the x-axis. I'm going to have some positive decreasing continuous function f of x. And I want to find on my x-axis, we would be able to zoom in to n plus 1, n plus 2, n plus 3, and so on. And if I'm looking for the first rectangle to have area a sub n plus 1, following what we did with our integral test before, I note that a sub n plus 1 is the y value associated to x equals n plus 1 for this function. So I want to choose a rectangle with that height and width 1. There are lots of ways I could place a rectangle with this height and width 1 on here. One way I could do that is to choose to move out rightward by 1 unit. Then this rectangle would have area a sub n plus 1. If I do a similar thing, this would have area a sub n plus 2, a sub n plus 3, and so on. And I could continue this process indefinitely, and it would have the infinitely many terms included in the E sub n summation here. Now, what does this tell me about my error? My goal is to try to compare it. And what I want to point out that I think is often confused is the fact that when I refer to error here, keep in mind that we're referring to E sub n, which is actually equal to the sum of the area of these rectangles. And that's important because I think it's tempting to think that the error is instead the mismatch between the area under the curve and these rectangles, because when we looked at Riemann sums, that is the way we were interpreting error. But here, error is what is represented by the entire rectangle itself. Put this back here. So when I'm trying to compare this, I'm going to say then that E sub n, which equals the green rectangles, I notice that the rectangles are larger, so these are bigger than the area under the curve. And in order to decide my bounds, it's significant to notice the x values that my rectangles sit over. The leftmost edge starts at n plus 1, and we assume, again, that this continues indefinitely. So it's really this area I'm comparing it to. We can do a very similar thing, in fact, to find instead an upper bound on E sub n. This is going to involve me sketching very much the same f of x. And keep in mind that I'm still trying to represent the very same E sub n. However, I can represent those same rectangles in a different way. So what do I mean by that? If I, again, situate myself on these axes so I can be near n plus 1, much like I did in the picture above, my first goal is to find the first term of my desired sum, which is a sub n plus 1. That's this vertical distance. And I want to draw a rectangle that has that height and width 1. Before, I chose to do so by finding this point and moving rightward by 1 unit. Instead, let's move to the left. Now this rectangle has area a sub n plus 1. If I do a similar thing, this rectangle has area a sub n plus 2, and so on. And what's significant here is that the rectangles I'm drawing here are exactly the same rectangles that I drew in the previous picture. So let's give them the same color to kind of emphasize that point. The difference is it's as if I started with the picture above, took all of those rectangles and simply picked them up and moved them to the left by 1 unit. And again, this would continue on. By taking those rectangles and shifting them to the left by 1 unit, notice that while before they jutted out from the curved area, now they sit underneath the curve. So in this picture, what I want to observe is that, once again, the error is exactly equal to the green rectangles. But now I see that that is bounded above by the area under the curve, but my bounds are different. While this upper limit is still infinity, notice that the leftmost value on the x-axis is n here. So what we're finding is that putting these together, these two pictures and these two results, leaves me with both an upper and a lower bound. So if I want to bound E sub n above, we have the integral from n to infinity. But if I want to bound it below, we have the integral from n plus 1 to infinity. Importantly, in drawing these pictures, I very much took advantage of the fact that f of x was positive, continuous, and decreasing. So this means that this is not always true for error. It is only in the instance when I'm able to apply the integral test that I can come up with these lower and upper bounds. In the next video, I want to take some time using this formula for these bounds to apply them to certain situations so we can see this in practice.